Hello everyone, today is day 3 of CodeDrift and now we are going to solve the problem reach the end.
So now let's begin with reading the problem statement. In this problem, Alice believes in the flat earth theory and he believes that earth is a 2D n cross n matrix and denoted by a matrix A where each element denotes the height at that place. Alice lives at 1,1 and want to meet Bob who lives at n cross n, but Alice is very lazy and don't like climbing. Can you tell if Alice can go to meet Bob without climbing to any higher heights? Return 1 if he can, 0 otherwise. Note he can jump down or walk on level ground. And constraint on this problem is that n is from 2 to 500 and a of I, j, which is the height of each place, is from 0 to 10 to the power 6. Now let's take this example of n equal to 4 and a equal to 20, 30, 14, 15, and second row of a equal to 19, 15, 15 and 16, and third row equal to 6, 18, 13 and 12, and fourth row equal to 20, 12, 2 and 5. So what does this mean is that the grid is 4 cross 4 and the height at the first place is 20, at the second place 1 cross 2 is 30, and at the third place 1 cross 3 is 14, and so on. And in this problem we want to go from this location to this final location, and you can jump from one position a comma b to another position c comma d if a comma b and c comma d are adjacent and a of a comma b
Is greater than or equal to a of c comma d.
Now let's create another matrix B of size n cross n where each element will denote that whether that cell is reachable from 1, 1 or not.
Matrix B will also be used to mark the cells as visited. If a cell is visited once, we will not visit it again.
Now let's create a stack. This stack will store all the nodes that we have to consider in future. So we can jump from one location a comma b to another location c comma d if those locations are adjacent. It means that they are sharing an edge, and a of a comma b
Is greater than or equal to a of c comma d.
So as long as stack has elements, what we will do is we will pop the last element and we will consider its neighbor. So now only 1, 1 is there in the stack, so we will pop this and consider its neighbor. So from 1, 1 we cannot visit 1, 2 as 30 is greater than 20. So this is eliminated. And from 1, 1 we can visit 2, 1 as 19 is less than 20. So we will mark this location reachable in matrix B and push that value to our stack. So we'll push the location 2, 1 to our stack. Now we will pop the last element from the stack, which is 2, 1 and consider its neighbor. So from 2, 1 we can visit 2, 2 as 15 is less than 19, and we can also visit 3, 1 from 2, 1 as 6 is less than 19. So now we will mark both the locations in our matrix B as reachable from 1, 1 and push those locations to our stack. And now we will pop the last element from the stack, which is 2, 2, and from 2, 2 we can visit 2, 3, and we cannot visit 3, 2 as 18 is greater than 15. So we cannot make this transition. So we will make 2, 3 as reachable in matrix B, and we will write 2, 3 back in our stack. Now we will pop the last value from our stack, which is 2, 3 and consider its neighbor. So from 2, 3 we cannot go to 2, 4 as 2, 4 is greater than 2, 3, but we can go from 2, 3 to 1, 3 as 14 is less than 15, and we can also go to 3, 3 from 2, 3. So we will mark both these locations as reachable in matrix B and write this location in our stack. Now we will pop the last element from the stack, which is 3, 3, and from 3, 3 we cannot go to 3, 2 as 18 is greater than 13, but from 3, 3 we can go to 4, 3 and 3, 4 as 12 is less than 13 and 2 is also less than 13. So we will mark both these locations as reachable from 1 in matrix B and push these two values in our stack. So we will write 3, 4 and 4, 3 back in our stack, and now we will pop the last element, which is 4, 3, and from 4, 3 from here we cannot go to 4, 4 as 5 is greater than 2, and we cannot go to 4, 2 as 12 is greater than 2 as well. Now we will pop the last element from the stack, which is 3, 4. From this location we cannot go to 2, 4 as 16 is greater than 12, but from 3, 4 we can go to 4, 4 as 5 is less than 12. We will mark that location as reachable in our matrix B and write those coordinates back in our stack. Now as we can see that the last location is reachable from 1, 1, but still let's go on iterating as long as there are elements in our stack. So now we will pop the last element from the stack, which is 4, 4, and we will delete it from the stack. And now let's try to visit its neighbor. From this location 5,2 we can go to 4,3, but 4,3 is already visited, so we will not write that back in our stack. And now let's pop the last element from the stack, which is 1,3. From 1,3 here we cannot go to 3,4 as 15 is greater than 14. And now let's pop the last element from the stack, which is 3,1. And from 3,1 we cannot go to 3,2 or 4,1 as both the values are greater than 6. So in the end, all the locations which are reachable from 1,1 are marked as 1 in matrix B. So this location, these three locations, this, and this locations are reachable from 1,1. And if this last location is reachable from 1,1, then Alice can go from 1,1 to n, to meet Bob. This problem is very much similar to BFS, DFS or any graph traversing algorithm. Here the order of exploration doesn't matter, so any algorithm that traverses through all the nodes as long as those nodes are reachable will work here. Now let's go through the solution code once. So in the solution code we are getting matrix A as our argument. Then here we are creating the stack, and here we are creating the 4 direction in which we can move. So from coordinate I, j we can go to I plus 1, j. So using this we can go to I plus 1, j, and using the second minus 1 and 0 we can go to I minus 1, j, and using the third coordinate 0, minus 1 we can go to I, j minus 1, and using the last coordinate 0 and 1 we can go from I, j to I, j plus first. And after that we will store the length of matrix A in n. After that we will create a visited matrix. This matrix will store whether a coordinate has been visited or not, and we will initialize our stack by appending 0, 0 here, and after that we will mark 0, 0 as visited. Now as long as stack has element, what we will do is we will take the last element, then we will pop the last element, we will make the last element as visited, and now we will go to its 4 neighbor. So first of all we will compute the new coordinate. So here we are computing the new coordinates of an adjacent element. After that here we are checking whether the neighbor is still in the grid or not. After that we will check whether that neighbor has been visited or not, and we will check if it is not visited, then check its value must
Be less than or equal to
the value of the current node, and if all the conditions are satisfied then append that neighbor to our stack. In the end, if the last cell, which is n-1, n-1 is visited, then return 1, else return 0. Now let's analyze the time complexity and space complexity of our solution. So the time complexity of our solution is O of n square, where n square is the size of the grid. So this time complexity comes from this step here, because there are n square location and each location can have at max 4 neighbors, and each location can be pushed by either of its neighbor. So this statement will be executed maximum 4 into n square times. And the space complexity of our solution is also n square, because we are creating a visited matrix here, and this matrix will be n square in size.
Now we will solve the second problem, optimal construction. Now we are going to solve the problem optimal construction. Now let's begin with reading the problem statement.
In this problem, there are n animals which are standing on positive x-axis. They are looking for food, so the government decided to build some shelters in their way so that each animal can reach any one of the shelters. So your task is to build exactly B shelters on the positive x-axis so that total distance covered by all the animals will be minimum. Distance between 2 points A and B is given by the absolute difference between A and B. Note, you have to minimize the sum of distances covered, not the individual distance covered by each animal. Animal can only move in left to right direction, means only in the direction of positive x-axis. Constraint on this problem is that n and b, which is the number of animals and number of shelters to be built, is from 1 to 200, where b is always less than n, and ai, which is the coordinate of each animal, is from 0 to 10 to the power 9. Now let's take an example. Now let's take this example of n equal to 7 and a, which is denoting the location of all the animals, equal to 3, 8, 6, 10, 4, 1 and 15, and b equal to 3. So what does this mean is that there are 7 animals, and the first animal is located at location 3, and the second animal is located at location 8, and the third animal is located at location 6, and so on. And we want to build exactly 3 shelters so that each animal can reach at least one shelter. As per the given constraint, all the animals can go from left to right direction, so that here on the x-axis I have shown all the animals. So this 6 here denotes that the sixth element is present here at location 1. So this 1 here denotes that the first element is present here at location 3, and this 5 denotes that the fifth animal is present here at location number 4, and the third element is present at location number 6, and so on. And all the animals can go from left to right direction as per given in the problem. So by looking at the diagram, we can make few observations. The first observation we can make is that all the shelters in the optimal case will be built at the location of some animal, and this observation can be proved by this example. Let's take this example that there are 3 animals and 1 shelter to be built. So if we build our shelter at a location which is not occupied by some animal, then our final answer will be the sum of length of all these blue line. And if we build our shelter at some location already occupied by some animals, then our final answer will be the sum of the length of these blue lines. So we have improved our answer by building a shelter at the location of some animal, and in the optimal solution all the shelters will be built at the location of some animals. So the second observation that we can make is that the shelters will divide the locations of all the animals in some subsegments. So what does this mean is that an animal will never cross a shelter without using it. So this animal will never cross this shelter to use this shelter, and this animal will never cross this shelter to use this shelter. It will never be optimal. So all the animal will always use a shelter which is just to their right, and it will never cross it. So all the shelters will divide all the animals in some subsegments. With the help of above two observations, let's try to develop some dynamic programming solution to this problem. For that, let's rewrite the array A. So A was equal to 3, 8, 6, 10, 4, 1 and 15, and B was equal to 3. So now first of all, let's sort this array. So after sorting, A will be equals to 1, 3, 4, 6, 8, 10 and 15. Now let's try to create some two-dimensional dynamic programming where dp of I comma j denotes what is the minimum cost of building j shelter for first I animals. Now let's take an example to understand how we are going to make transition here. Let's consider that we want to compute dp of I comma j. So what we will consider is that we have built a jth shelter here, and we have to build j minus shelter before this location. So what we will do is we will consider a barrier, and we will consider that j minus 1 shelters are constructed before this location, and all the animals that came after this barrier will come to this jth shelter. And this is how we are going to make transition in our dynamic programming. More precisely, to compute dp of I comma j, what we will do is we will consider all the k's less than I, and dp of I comma j will be equal to minimum of dp of k comma j minus 1 plus the cost. So this cost will be cost of all the elements which will travel after that barrier to the ith location. So it is the cost of all those animals that we have to consider separately. Now for the example we already considered, after the sorting, A will be equals to 1, 3, 4, 6, 8, 10, 15, and B was equal to 3. Now we will build one shelter here, another shelter here, and another shelter here. So our final answer will be equals to this animal will travel from this position to this position, and the first animal will travel from this position to this position, and this animal will travel from this position to this position, and this animal will travel from this position to this position, and the last animal will not travel because it has a shelter at its own position. So from that our final answer will be equals to 1 plus 3 plus 4 plus 2 plus 0, and our final answer will be equals to 10, and this will be our final optimal answer. Now let's go through the solution code once. So here in the solution code we are getting a and b as our argument. After that we are storing the length of a in n, and then we are creating a two-dimensional dynamic programming dp of dimension n plus 1 to b plus 1. So this 10 to the power 12 will act as an infinity in our dynamic programming. It means that this dynamic programming value does not exist, and dp of 0, 0 is initialized to 0. This will act as a base case in our dynamic programming. After that we are sorting the coordinates of each animal. After that we are iterating for I from 0 to n, and for k from 1 to b plus first, and we are creating answer variable into 10 to the power 12 and sum equal to 0. So what we are doing is we are considering some prefix up to some I, And after that we are considering that we want to build k shelters till this ith animal. Then we will iterate for this j from I to 0 in reverse order, and we will consider that we have built k minus 1 shelters up to this jth animal, and then
Build kth
shelter here at this coordinate, and all the animal in between will go to this shelter, and all the cost of these animal here will be stored in the sum variable. And we are also updating this sum variable here in this inner for loop. After that we are storing the best answer in dp of I plus first to k, and at the end our final answer will be stored in dp of n comma b, because we want to build b shelters for first n animals. So that will be our final answer, and in this statement we are returning it. Now let's analyze the time complexity and the space complexity of this solution. So the total time complexity of our solution will be O of n cube, where n is the total number of animal, and this time complexity comes from these three for loops, this for loop, this for loop, and this inner for loop. The first for loop goes from 0 to n, the second for loop goes from 1 to b, and for the third for loop it goes from n to 0. So the total time complexity of our solution will be O of n cube. So the overall space complexity of our solution will be O of n square, because we are creating an n cross n matrix to store dynamic programming values. Thank you for watching. Please like and subscribe and stay tuned.